Hello and welcome back to the second session of ICFP 2020. And our next paper is going to be sealing pointer-based optimizations behind pure functions. And it's going to be presented by Daniel Salzman.
Hi everybody, my name is Daniel Salzman from Microsoft Research. I'll be presenting joint work with Simon Hudon from Carnegie Mellon and my colleague Leonardo Demura from Microsoft Research. Our paper is titled Sealing Pointer-Based Optimizations Behind Pure Functions. Now, functional programming really shines for interactive theorem provers for many reasons. It's easy to encode terms with inductive types, and this is actually surprisingly cumbersome in C++. It's easy to traverse terms with higher order combinators. For example, easy to write functions that replace subterms of terms or find subterms matching patterns. And it's easy to backtrack using persistent data structures. So we can just snapshot the world, try tactic 1 in that world, and if it fails in constant time and no extra programming effort, we can just roll back the world to the snapshot before we started tact 1 and then try the second tactic in it. And as we would expect, most interactive theorem provers are written in functional programming languages. So Isabelle Hall is written in PolyML, Coq is written in OCaml, Agda and Idris are written in Haskell, and Lean 3 was written in C++ at great spiritual cost, but Lean 4 is being rewritten in Lean 4 itself, which is a functional programming language. But while functional programming shines in this domain, pure languages suffer a critical limitation that we call purity's Achilles heel, which is that traversing a term requires time proportional to the tree size of the term as opposed to its graph size, which causes exponential blowup in theory and in practice. And here's a little illustration. On the left, there's a term whose DAG representation has only 4 nodes, and in fact, has only 4 nodes in memory. But when you view it as a tree, it has 2 to the 4 minus 1 nodes. So exponentially more nodes in its tree representation than in its graph representation. And perhaps a surprising empirical finding is that terms with astronomical tree sizes are actually extremely common in interactive theorem provers. So it's well known that even basic operations can produce them. So unifying two terms where the function symbol has arity n can produce a term whose tree size is 2 to the n. But this is a somewhat contrived example. But in reality, terms are often the result of long chains of somewhat arbitrary user-written metaprograms or tactics. And at least in Lean's mathematical library MATLib, it's not uncommon for a proof that has only 20,000 nodes in its DAG representation to have over 2 billion nodes in its tree representation. And many performance issues in Coq and Lean, going back many years, have been the result of improper handling of such terms, despite having the needed impure tools at hand. Basically, the exponential blowup is so severe that if a single module ever traverses a term with insufficiently precise caching, it's very likely going to be a bottleneck. And now we can talk about our contribution. So we present a new way to, quote, seal the needed optimizations, the optimizations that you need to traverse terms in linear time. We show how to seal these optimizations behind pure functional interfaces. And here is the main idea. We start with a pure reference implementation of something that we want to optimize. We find sufficient conditions for a particular optimization to respect the reference implementation. We then create a new primitive that takes these conditions as preconditions using dependent types, and otherwise is given the nominal pure reference implementation. And then we just compile this primitive into the optimized version. And a simple meta-theoretic argument establishes that since it was proved, since the preconditions were proved, the optimization is sound. And we show how to do this for several common low-level optimizations, including pointer equality tests and even direct pointer address manipulations. And we show how to use these new primitives to traverse terms in linear time, which is the problem we set out to solve. So perhaps the simplest pointer optimization is just short-circuiting equality tests using pointer equality. And the idea is simple. If two terms x and y have the same memory address, they must be structurally equal. So you can skip the potentially exponentially expensive structural equality test and just return true. And the challenge here is that this optimization is only sound in general for reflexive relations. And the solution is somewhat simple. Allow the optimization for any relation that you can prove is reflexive. Which brings us to our first new primitive, which we call with pointer eq. And now with pointer eq takes two terms, x and y, of type alpha, and a thunk k that takes a unit type and returns a bool. And the precondition h is a proof that if x equals y, then this thunk k is going to return true. And then the overall primitive with pointer eq returns a bool. And its pure reference implementation just simply evaluates the thunk. And now the compiler will treat this as opaque until reaching the low-level IR, at which point it will expand a call to with pointer eq to the following pseudocode snippet. It first checks if the pointer addresses are the same of x and y. If they are, it returns true. Otherwise, it evaluates the thunk. And the precondition h guarantees that this version respects the pure version by a very simple argument. Now, with pointer eq alone already can yield exponential speedups on pointer equal terms, trivially. But small deviations from pointer equality remove the benefit entirely. So this is an illustration of two terms that pointers share an enormous tower, but their heads are actually different. So they are not themselves pointer eq, even though their children are. So with a single call to with pointer eq will just see that they're not pointer equal and fall back on recursive structural equality. Obviously, what we want is to call with pointer eq recursively on the children, and we can do that. The construction is somewhat elaborate, but it's entirely mechanizable, requires no new primitives, and the paper goes into the details for those who are curious. Now we're almost ready to traverse terms in linear time. Consider the naive exponential time algorithm to evaluate a simple arithmetic term into a natural number. So pretend we have a term type that has two constructors, one and add. So we can just evaluate this into a net by mapping 1 to the numeral 1, and by evaluating add t1, t2 by first evaluating t1, then evaluating t2, and adding the results together. Now, we're going to show how to use with pointer eq, the recursive version, to build a linear time version of this algorithm. We need two additional components. We need constant time intrusive hashing, and we need something that we call sharing the common data, which I'll discuss shortly. So it's almost hard to believe, but even just computing the hash of a tower requires exponential time. But hashing, unlike equality, is a unary function. So in principle, we can compute it once and just store it somewhere, which brings us to this folklore trick, which we call intrusive hashing, which is to simply extend the term type itself to store the hashes of the terms as extra arguments to the constructors. So here, the third argument to add is an adder, which is just our type that represents hashes in this case. And we can write a fast constant time hash function that simply projects out this hash field. And we can write a smart constructor that internally calls the built-in constructor, but will compute the hash automatically using the fast hash on the children. Now, Lean4 has reference counting and destructive updates, so we can actually use imperative hash tables and get the desired expected big O of 1 lookup times. But if your language does not have this feature, then you can still use functional or persistent hash tables, and then all of the same constructions apply, but every time we say linear, it really means quasi-linear for you. Now, the semi-naive traversal, we call eval fast eq fast hash, which is to use the recursive with pointer eq test for the equality, and to also cache using the constant time intrusive hash and a hash map. Now, this is already linear time on this example, strictly because of the recursive with pointer eq, and because of the intrusive hash cache, it's also linear time on this example in expectation, because with high probability, the hashes are going to be different, and in the small chance that they're the same, they're very unlikely to be the same again for the children, and so on. But this semi-naive algorithm is still exponential time on this example, where we have two structurally equal terms that are pointer disjoint. And this brings us to sharing the common data. So with low-level pointer manipulations, we can, quote, share the common data in linear time. And what we mean by that is to take a term like this that has multiple subterms that are structurally equal but pointer disjoint, and simply share the common data or compact the term and produce the term such that equality implies pointer equality of all subterms inside the term. And now in the paper, we introduce additional primitives that allow writing pure versions of this procedure from first principles in linear time. But Lean, as part of the Lean runtime, we already have a high performance version of this procedure that applies to objects of any type. So there's no additional trust required to simply expose it. So we present a new primitive, share common, that is just the identity function, whose reference implementation is just the identity function, and actually takes no additional preconditions, but under the hood, it's going to share the common, use the runtime support to share the common data inside X. And finally, we have a robust linear time traversal, which we, to be overly pedantic, call eval fasteq fast hash share common. And the idea is simple. We first share the common data, which takes linear time. And then we call eval fasteq fast hash, which is linear time as long as the data has been maximally shared. And our motto in general is if terms are equal, they should be pointer equal, and they will definitely be pointer equal after share common. And if terms are not equal, their constant time hashes should not be equal with high probability. Now, the paper covers many extensions and alternatives to this approach. I'll go through a couple examples very briefly. So we can have a pointer equality test without requiring reflexivity as follows. Here's a primitive with pointer eq result that takes two terms x and y. And instead of a func k, it's a continuation that gets to see an optional proof that x equals y. But instead of returning a Boolean, it returns an element of any type beta. And now the precondition we need is that no matter what proof we give it, or what optional proof we give it, this continuation is going to return the same value. And the reference implementation just calls it on none. But at runtime, if x and y are pointer equal, we call it with the proof of reflexivity. And we can also support direct pointer address manipulation with the new primitive with pointer adder, which takes a term x, whose address we want to inspect, and it takes a continuation k that is going to look at that address and again return an element of an arbitrary type beta. And the precondition we need here is that no matter what address we give k, k returns the same value, and then the reference implementation just evaluates k at an arbitrary value, 0, whereas the optimized version will evaluate k on the actual memory address of x, and the proof very trivially implies that the optimized version is functionally indistinguishable from the pure reference implementation. Perhaps the surprising part of this is that this precondition isn't too restrictive. And we show in the paper that indeed we can do many, many sophisticated constructions using with pointer adder. And in fact, combining with pointer eq result and with pointer adder, we can implement pointer caches from first principles, and we can implement share common from first principles, and so forth. But we recommend the fasteq fast hash share common approach in general. It gives very good performance in all our use cases in practice. It's simple, and the other constructions are significantly more elaborate for very little payoff. And thank you. That's all we have time for today.
Right, thank you, Daniel. So if you're interested in joining the authors for a live Q&A and you're in the New York time zone, then click on the link in the Slido page for this paper.